Hello everyone and welcome to another Stat 437 lecture video. In today's video, we're actually done talking about different types of models for longitudinal data. So we've gone through marginal models for linear data, we saw marginal models for other types of outcomes, we saw linear mixed effects models, and then most recently we just looked at transition models where we have categorical or binary data, and we worked through computing the transition probabilities there using standard logistic regression. So we've seen a bunch of different ways of fitting longitudinal data to different models, and we've interpreted those models, we've test hypotheses with them, we talked about some of the strengths or the weaknesses, and in the following lecture, after we're sort of done talking about today's topic, we'll go through and we'll review everything that we talked about with longitudinal data before we start talking about survival analysis. Now, survival analysis isn't really distinct from longitudinal data. It's a sort of a specific type, and so we'll see more modeling there. But in terms of, following one response over time and just fitting data or models to that, with what we've done so far, you actually have quite a wide range of tools to accommodate that. Now, one thing that we have not sort of dealt with at all is looking at the realities of what these data look like in the real world. And one of the most common issues you're going to run into if you try to take the methods that we've been talking about in this course so far and apply them to real world data sets is that oftentimes data are really messy. And probably the most common way that these data can be messy is through missingness, right? So you're going to have responses that you've just should have collected for an individual, but they're not in the data set. And how do you deal with that? So that's going to be the focus of today's lecture and of the next lecture, where we sort of look at missing data for longitudinal models, both sort of in concept and in practice. I'm going to ignore doing a full theoretical deep dive of this material. I'll post some supplementary notes that explore what we're talking about with a little bit more depth. The only reason I'm not doing the theoretical deep dive is because you could realistically have an entire course just on the methods that we're going to talk about here. And I think it's better to introduce them to you so that you have them in your toolbox and then show you how to actually go about using them in R than it is to try and do a full theoretical underpinning. If you're interested in this, there's plenty of good books out there to learn about missing data, or you can feel free to ask me and I'll sort of point you in the direction of material that you might be interested in. But for now, if we can understand conceptually what we're doing with missingness, and then in the next few lectures talk about sort of practically how to go about that, that's what we want to be doing. So with that, I can open up the slides here, and we can talk about missingness in terms of longitudinal data. So in the most recent lecture, we analyzed these data which came from the financial crisis study, right? And the data looked sort of like this, right? We had an ID, we had their age, we had a number of other baseline factors. And then we saw these outcomes, Y2, Y3, Y4, and so on, right? Now, these were the data that we analyzed. They started with ID number 10, the second person had ID number 17, third person had ID number 29. If you were paying, close attention to that, that may have seemed strange to you. And the real reason that would have seemed strange was because, in actual fact, we collected a whole lot more data than just that. Okay, so the real data that were collected had additional individuals being measured. And you can see, for instance, ID2 was excluded from our data set, and that's because ID2 did not have measurements at time 6 and at time 8. We have NAs there for not applicable, not a number, right? ID 11 was missing almost everything except for at times 6 and 7. And so if you actually looked at any of the real data sets from the course, if you download them from their true source, oftentimes you're going to see these types of patterns emerge where there's lots of missing data in longitudinal studies. And some of this is because it's hard to follow people for long periods of time. Missingness is a problem sort of across statistics, but it's a particularly large problem in longitudinal studies. And so it's worth asking, when we analyzed the data that just ignored this, right? We just took all of the people who completely responded as compared to the true data that were collected, what did we lose? What were we giving up? And so missing data refer to any observations which we wanted to collect, which we had some intention of collecting, but which we did not record in the file for absolutely any reason, right? So whether we didn't record them because we didn't actually observe them, or if we didn't record them because, the paper that we wrote their response down on got destroyed, or if we didn't report them because they decided that they didn't like our study and they left, right? Any reason that they're not reported is considered missing data. And it's a pervasive problem across all of statistics. Any data set you download is likely going to have missingness in it, but it's particularly common in longitudinal studies. And that sort of makes sense if you think about, you start following someone when they're 10 years old, trying to keep someone in sort of the study location for a period of 10 years. Well, people are going to move away. People are going to die of other causes. People are going to lose interest in helping you out. And so it's a particularly big problem for longitudinal data. So when we're talking about missingness, generally speaking, we want to talk about the classification of how this missingness came to be, and then we can explore different methods depending on how we classify it, right? And different types of missingness are going to be a bigger problem than others. So you can think sort of intuitively, if you had, a piece of paper that you were recording responses on, if some of those papers get randomly destroyed, right, then that doesn't really have anything to do with the underlying process, right? It's a shame that you're missing that data, but that doesn't have anything to do with the process itself. Whereas if you imagine that, someone who starts having really bad outcomes from a study, right, someone who has really severe side effects, if those people become more likely to drop out of your study, well, now suddenly we're biasing the results, right? Because the people that are left in the study are those who happen to be responding well to the treatment. And so if you're only analyzing the people that you take all of the responses for, well, all of the people who would have had negative responses dropped out of your study, and you're just left with a positive sample, right? So we have to be really careful about where is this missingness coming from. And in order to do that, we can talk about sort of classifying different missing data mechanisms. So to do this, we're going to define some notation here. And we take Rij to be an observation indicator. So in particular, if we make the observation, so if Yij is observed, then we set Rij to be equal to 1. And otherwise, we set it to be 0. So we assume that we observe this for everyone at all time points. And it just says 1 if we did observe that value, 0 otherwise. And so if we're thinking about Rij now as being a random variable, then the way that the missingness is being introduced is sort of the distribution of these Rijs. We're also going to assume for now that we're only concerned with missingness in the outcome, so in Ij or in Yij. In theory, you might have missing covariates as well, and those are going to be a problem. Some of the methods we're looking at will be able to handle those, others won't be able to, but for now we're just going to be thinking about missingness in the outcome. So we're going to, by way of notation, partition the outcome yi into yio and yim. And so this yio is going to be the observed component, and this yim is going to be the random, or the missing component, sorry. And we're thinking about these as both being random variables, but it's sort of up to us to decide, are their distributions the same, right? So yi has some distribution that we're assuming, but maybe the observed values and the missing values follow different distributions. So, thinking about that situation where the individuals who are responding poorly have missing values, well, then YIM is going to sort of be a worse distribution in terms of the outcome than YIO is going to be, okay? So that's just the notation there. In terms of introducing actual sort of missing data types, we tend to think about this as this hierarchy, okay? So in the best case for us is when we can say that the data are missing completely at random, and we abbreviate that as MCAR or MCAR. So MCAR data, we define them based on the probability of those missing indicators. And if we can say that given the observed, the missing, and any additional covariates, if the distribution only depends on those additional covariates, so it doesn't depend on the outcome at all, then we say that the data are missing completely at random. And the reason it's completely at random is because it doesn't have anything to do with the outcome. It's completely random as far as the outcome is concerned. So, for instance, if we're in the situation where we're talking about a hard drive failure as being the cause of certain missing data, right? Maybe we have a bunch of different researchers who are collecting data samples on patients, and one of them, drops their laptop in a lake. that data is going to be completely random as to what's missing, right? Those individuals are going to be representative of all other individuals. It's not going to be informative at all. We say it's missing completely at random. And that's ideal. If it's completely at random, we're going to see that we can basically just ignore it. Now we say that data are missing at random, and we abbreviate that as MAR or MAR. If instead of it being totally random here, it only depends on the things that we observe. So the conditional distribution given the observed, the missing, and the additional covariates only depends on the observed and the additional covariates. So in other words, the missing values are not informative as to the missingness mechanism. Okay? And so, for instance, let's say that you have a study design where you're trying a new experimental drug out, right? And you're trying to see, does this help the outcome? Well, maybe what you're doing is you're saying anyone who observes too high of an outcome over time gets removed from our study because we need to give them a treatment that's actually going to be helping them. Okay, so, if it's blood pressure medication, we know that we have good medication that exists, which sort of keeps your blood pressure regulated at a level. If you're trying a new blood pressure medication and there's a patient who observes, blood pressure that's too high for consecutive periods, you might remove them from their study on ethical grounds to say you need to be assigned to a treatment that's actually going to work for you. And so in that case, we know from their observed values, say at time 1, if their blood pressure is still too high, times 1 and 2, then we've removed them from the study. And so we can predict whether or not they're missing on the basis of only the values we've observed, right? So we have missing completely at random, doesn't depend on the outcomes at all. Missing at random only depends on the outcomes that we've observed. There's, sort of one final obvious way to add on to this, and that's to say that data are not missing at random. And we abbreviate that NMAR. You'll also sometimes see MNAR for missing not at random. They sort of interchangeably used there, right? And so if you have, say, individuals who smoke, they're less likely to continue to respond to your smoking questionnaire. Well, then that's going to be an example of data that are not missing at random, because the missing values, the amount that someone is smoking, tell us whether or not, or are predictive as to whether or not they actually responded. And so you can see this as sort of being a hierarchy, right? So data which are missing completely at random also satisfy the properties for missing at random, and data which are missing at random would also similarly satisfy the properties for not missing at random, which is this sort of distribution is the one that we're working from, right? But intuitively from our perspective, we'd prefer data to be missing completely at random if they're going to be missing at all. If they're going to be not completely at random, then we hope that they're missing at random, and otherwise, we're sort of left stuck with dealing with data which are not missing at random. And so we're going to think about those as sort of 3 layers. And also, for the most part, we're really only dealing with completely at random or at random data, not because those are the most common, but because those are the ones that we can address the best, right? So sort of out of necessity. Now, in addition to thinking about the mechanism, we can also think about some patterns of missingness, right? So here I have sort of 3 different data sets, and we can just look at these top row for now. And the idea is that in these red marks here would be observations that we didn't make. So these are missing values, right? And there's a few different patterns that we have going on here, okay? And the pattern of missingness is also going to turn out to be somewhat important. So in this first example, we have what is called a dropout pattern. And the idea there is that someone starts in the study, right? We make some observation for them, and then eventually they drop out of the study. And once they drop out of the study, we make no more observations for them, right? So the second person, we observe up to time 4, and then they've dropped out. These next 2, we observe the whole time. This person, we observe up until the end of time 3, and then they're gone forever. Okay, so a dropout pattern is quite a nice pattern to deal with, because once someone is gone, we know that they're gone forever. And so we just sort of need to predict their first dropout section. Now, the second pattern is not a dropout, right? Because, for instance, there's this person, they're missing at time 4, and then they come back and we see a value of them at time 5, right? But we can call this pattern monotone. And the reason that we can call it a monotone dropout pattern is because if we rearrange the columns a little bit, we see something that looks like dropout, right? So if we move column 4 down to where column 5 is, we move column 3 to where column 4 was, and then we move column 5 to where column 3 was, right? So we sort of are swapping those 3 columns around there. Then we get this pattern down here, right? So we have 1, 2, 5, 3, 4. And in this case, you can see now we have this dropout pattern, right? So as soon as we have someone not being observed, then they're never observed again. And then for everyone else, they're fully observed, right? And so it looks as though we have this dropout just by rearranging. And so we call that a monotone missing pattern because we can sort of order the columns in such a way so as for it to be monotonically increasing. Dropout patterns are, of course, monotone because that's sort of how they're defined. Now, this last pattern here is one which is non-monotone, right? So it looks quite similar to the missingness that we have in the second case, except if we try to rearrange it, and, I'd encourage you to do this yourself, you're always going to find that there's going to be some individual who drops out for a period, is reobserved, and then drops out again. Okay? And so because of that, this is not a monotone missing pattern. And it's going to turn out that monotone patterns are a lot easier to deal with than non-monotone patterns. And that's just going to be because of a sequential modeling procedure that we'll see. But when we have monotone missingness, we're happy because it's easier to deal with, right? And so we can either think about the mechanisms or we can think about the patterns of their missingness. So, we've talked a lot about sort of classifying missingness now, but it's probably worth taking a moment to ask, why do we even care? What are the impacts of missingness? I think intuitively you'd get the sense that missing data are going to be a problem, but, in what way are they a problem? And so we can ask, what happens if we ignore the fact that we have missing data? So in the previous analysis, when we were doing the modeling of the financial crisis data, we did a complete case analysis. So a complete case analysis occurs when we just ignore any missingness and we only keep the people that we have all of the observations for. Okay. Now it turns out that a complete case analysis is valid if the data are missing completely at random. So if your missingness is not at all informative about the outcomes, then you can just do a complete case analysis. However, you might not want to. And the reason that you might not want to is because they're going to be unnecessarily inefficient, and it's only valid when the data are missing completely at random. So what do we mean by this? Well, if you think about it, when you only keep the complete responders, you're throwing away a lot of observations that were partial responders, right? So if 50% of your data has at least some missingness, you might be throwing away half of the responders, even if they're only missing a little bit. And so that's throwing away a lot of information. You're going to end up with more variability in your results than you would need to otherwise. You're essentially artificially limiting your sample size. The other issue is that we can't actually test whether data are missing completely at random. There might be a good reason to suspect that they are, again, thinking about sort of a hard drive failure scenario. But in the absence of that, this is a very strong assumption to be making. And if we're wrong about that assumption, if the data are not missing completely at random, well, then the results of a complete case analysis are totally biased, they're entirely unreliable, and we can't actually say anything about it. So we might turn to an available data analysis instead. So the idea with an available data analysis is that instead of only looking at the people who completely responded, we look at anyone, the full set of responses that they had, okay? And so if someone was responded, 70% of their responses were there, we consider those 70% of responses. So this is going to be more efficient than a complete case analysis. And if the data are missing completely at random, it's going to still be valid. However, there's a downside again, of course there is. This makes the data inherently unbalanced, right? So again, if you think about taking 10 measurements of people, right? Balanced data means that all of the individuals in your data set have those exact same 10 measurements taken. And, they're sort of at the same times. You can interpret, the first measurement of every person as being at each time. Now, if some people only have 6 of those 10 done, well, then those people are not going to be sort of corresponding to the balanced data assumption. And so any techniques that require you to have balanced data are not going to work. Any correlation pattern matrices that require balanced data aren't going to work, right? And so you're really limiting the types of analyses you can run using an available data analysis, okay? And again, we're still relying on that missing completely at random assumption. So if they're missing at random or if they're not missing at random, the available analysis and the complete case will not work. if you're using a likelihood-based technique, so the transition models and the linear mixed effects models, if you fit using those techniques, they're going to be valid whether you're missing at random or if you're missing completely at random, okay? And this is going to be true so long as the models are correctly specified. As long as you've correctly specified the likelihood, you're going to be valid under those first two situations. So that's great, right? That's a good thing to know. And that assumption about them being required to be correctly specified, well, we're already making that assumption to use those models in the first place. So likelihood-based procedures actually have some inbuilt resistance to model misspecification. But if we were thinking about something like the generalized estimating equations, that's not going to have that sort of resilience to missingness, okay? So in all other situations other than those listed here, for the sake of our course, they're going to be biased and unreliable, right? If you have any missingness that's not missing at random, then already you have an unreliable analysis. If you have data which are not missing completely at random and you're not using likelihood techniques and you haven't dealt with them in another way, biased and invalid inference, okay? And just like the way that it's going to be biased and the way that it's going to be invalid are not necessarily predictable, because that's going to depend on how is the data missing, what are the sort of actual models at play, everything else. And so you can't even say things like, we're going to be overly conservative or something like that, because it's just going to totally invalidate the analysis. It's like using the wrong tool for the job. And so it becomes a really big problem very quickly. So with that, what are some general techniques that we can use to handle the missingness in this data? So we're going to talk about sort of 4 families of techniques, and we've already briefly touched on 2 of them, so that's good. The complete case analysis is going to take just the complete responders in the data frame, right? So you just drop everyone who you didn't respond to fully. And as we already said, if the data are missing completely at random, this is valid. Now, in general, I'm only actually going to suggest that you do a complete case analysis if you're just trying to sort of fit some models to see if model fitting looks like it might work, okay? Not when you need any actual results, but if you're like, I just need to write some quick code here to make sure that I can fit data, then a complete case analysis might be valid. Slightly better is the available data analysis. And this is using all of the observations. So if you're using GEE, for instance, they're sort of built to use an available data analysis. You can take unbalanced data really easily. And this is going to be my recommendation if you're using if you're willing to assume missing completely at random. Using an available data analysis, if it's missing completely at random, is sort of okay. You're not going to be inefficient, but you need to have a really strong justification for why the data might be missing completely at random. In all other situations, you're going to be wanting to look at one of the remaining 2 techniques. So we have weighting techniques, and weighting techniques, essentially the idea is that we're going to be generating pseudo data sets where we weight each individual that we did observe to account for people who are like that person, but who we did not observe. Okay, so we're going to talk about these in a little bit more depth, but weighting techniques are one broad class for addressing missingness. And the last class of techniques that we'll talk about in detail is imputation techniques. And imputation techniques rely on actually filling in values for the missing data, right? So at their base level, what we're trying to do is predict the values that are missing, and if we've predicted them, we can fill them in and then pretend as though we actually had those observed. And if we adjust our standard errors, everything's going to work out nicely. Okay, so those are sort of the 4 overarching classes. The first 2, complete case and available data, should sort of only be relied on in extreme situations where you're just trying to do a quick analysis. But these weighting techniques and imputation techniques are both quite powerful, and we'll explore them now. Now, for handling not missing at random data, we're not going to talk about that at all for the rest of this class. And the general reason is that you need to model jointly the distribution of yi and ri, right? So you need to model the missingness alongside the observations. If you're not doing a model for yi, ri jointly, then you're not going to be able to handle this not missing at random data, right? And so As a general rule, the techniques are sort of beyond the scope of this course, but again, there's sort of a full literature on missing data if this is something that's interesting to you. Obviously, these types of problems are actually quite important to think about because not missing at random data happens sort of all of the time, right? So we're artificially limiting ourselves because we need to, start with what is easy, what is possible, but just, know that what we're talking about is not going to help us with not missing at random, and that's an important case to consider. So on to weighting techniques, right? We've talked briefly about dropout when I was, introducing the different patterns, right? And so dropout occurs when someone leaves the study and then does not ever return. And so we could think about defining this dropout indicator here, which is going to take a value that equals the last period of observation. So if we take 1 plus the summation of their observed indicators, right, then if someone is last observed at 0.3, right, then Rij is going to be a 1 for stages 1 and 2, and then it's a 0 after that. So Di is going to be 3, right? So it's the last point that they were observed. If someone's observed for the full study, then Di is going to be K plus 1, which sort of we read as they didn't drop out until after the study was already over, okay? But so if we have these Di terms, then we can start talking about dropout. And we're going to think about weighting techniques as being specific to dropout. They're not technically, you can use them when we're not using dropout, but they're going to be easiest to understand in this situation. So we can sort of conceptualize these weighting techniques as discussing the probability of inclusion in the sample, okay? So what we're saying here is we want to say that we have these probabilities, pi ij, and pi ij is going to be given by the conditional probability that the dropout indicator is after time j, given that we know it's at least at time j, okay? And we condition on I to sort of indicate that these can differ based on individuals. So what this is essentially saying is it's the probability that an individual lasts beyond time j if we know that they were already in the study available there, right? So if you wanted to know the probability that they last beyond time k, then you're saying what's the probability that they were fully observed in this study? The probability that they're observed past time 2, given that they were at least at time 2, is essentially the probability that they didn't drop out at time 2, right? So this gives the probability the individual I was still under observation at time j, assuming that they made it to at least time j minus 1. Now, any probability that we look at like this, you should think we could estimate this using logistic regression. And we could fit a model to estimate these probabilities from our data without any problem. And then the way we're interpreting this is that if you have a low pi ij, then you were unlikely to have been observed in our sample. And if you have a high pi ij, then you were quite likely to be observed in our sample. Okay? And so we can think about sort of a general population and our observed data. So on the left-hand side here, I have 100 dots that are representing the true population. And sort of we're thinking about them as two different types of individuals, right? And then on the right-hand side, we actually have the observed data. So in the observed data, these lighter circles, right, are going to be sort of the people that we did not observe. And the darker values, so given sort of here and here and here and here and so on, right, these are the values that we actually did observe. And so if you were to work this out, we have 100 people in this population, and 40 of them are blue, 60 of them are this magenta color. And of the blue people, we observed 20 values, and there were 40 total blues, and so they had a 50% chance of being observed, right? In the magenta individuals, we observe 3, there are 60 of them, and so they have a 5% chance of being observed, right? And so you can think about sort of on a bigger scale, our true population and our observed data are going to look something like this, right? We have classes of people who are going to be similar to one another. We're going to observe some of them. We're not going to observe others. But we could think about then taking our observed data and from our observed data, creating a pseudo population, right? So in our observed data, we said that we observed 20 blue individuals, but we know that there should have been 40 blue individuals. And so what if we just let each of these blue individuals count for 2 different people, right? So then each of the observed 20 counts for 2, and that gives us our 40, right? Similarly, we observed only 3 of these magenta individuals, and we know that there were supposed to be 60 of them, right? And so what if we let each of them count for 20, right? Then we're going to get 20 times 3 is 60 individuals, right? And so another way of actually getting to this is taking the inverse probability, right? So we knew that pi b, we estimated that to be 1/2. And so if you take 1 over 1/2, that gives us 2. And so if each individual counts for 2, then we've reweighted them up to this population, this pseudo population, where the blue individuals are as represented as they were in our true population. Same thing with the magenta. If we take 1 over 5%, that's going to give us 20. So if we rewrite each of these at 20 people, then we've reweighted them up to be 60% of the total population. And so in general, we could think about applying this to longitudinal data, where we take pi I to be the probability that an individual did not drop out of the study, right? So it's the probability that our dropout indicator is larger than k, which is actually just the product of all of our pi ij's, right? So if we take that probability, then if we go 1 over that probability, that gives us a weight, right? And it's an inverse probability weight. It says for people like individual I in our sample, they had a pi I probability of actually being observed at the end of our study, of having not dropped out at any point. And so, if that probability is 5%, then what we're saying is that for every 20 people that were like this person in our original study, we only observed 1 of them, 1 in 20. Similarly, if you had like a 90% chance of being observed, well, then for every 10 people in the original population, 9 out of 10 of them are still observed, right? And so what you can see that when pi I is low, our weight goes high. You have to count for more people because they were rare to actually see. But what that means is that there's a lot of people in the base population who we didn't observe at the end of the study, but who we should have observed at the end of the study. Okay? And so if we reweight and then we just perform a complete case analysis, then actually in this reweighted data set, we're going to find that whether the data are missing completely at random or they're missing at random, we get missingness properly accounted for. We have reliable results. This is assuming that our probabilities are estimated correctly, that these pi i's are correctly estimated. Okay? And the rationale for that is just that we've taken an observed data set, right? And by reweighting, we've made it look like our true population again. And so if we've reweighted that in the correct way, if each person is counting for the correct individuals, well then in a large enough data set, we're going to get consistent and unbiased results. Okay. Now, this was using the complete case analysis. We can actually do this slightly more efficiently. And that's instead of giving every person an individual weight, we could assign each of their observations that they actually had an individual weight, right? So if you think about, instead of using the probability that DI was greater than K, we could say at time J, what's the probability that DI was greater than J? What's the probability that dropout happened after time J? And that's just going to be the product of the probabilities up to and including time J, right? In the same way that that was true at time K on this last slide here, right? So we can do that just at each time J. And then if we take the inverse there, that's the probability that they were still in the sample at time J. And if we weight their observation at time J by that same value, then we're going to sort of be able to do this available data analysis, except keeping around more responders, right? So we're going to be able to keep more individuals in our sample that way. And that's going to provide sort of a more efficient way of correcting these estimators. So concretely, we can look at this using generalized estimating equations. Okay, so what we're going to do is we're going to define this weight matrix, this WI, to be a diagonal matrix, and it's going to be the full K dimensions, Ki dimensions. And on the diagonals, we're going to take the observed indicator, so Rij, and multiply it by that weight at time J. Okay? And so what that's going to mean is that if the individual was observed, the diagonal element is going to be this Wij. It's going to be their weight. And if the individual was not observed, we're going to have a 0. Okay? And so then we take this weight matrix, and then we plug it in to our GEE estimating equations, right? And so we have this DI prime VI inverse, and then normally we would just have this residual term here, but we multiply by this weight matrix, and by doing so, we're going to be sort of performing that available data analysis. And we call this inverse probability weighted generalized estimating equations, IPWGEE. Okay. Now, we either need xi to be fully observed or vi to be diagonal in order for this to work. Okay. Now, this isn't actually a big assumption because we don't need to correctly specify vi. And so if xi has missingness at all, then what we can do is we can just take vi to be diagonal, and then as long as our wi matrix is correctly specified and our mean structure is correctly specified, this is going to work with missing at random or missing completely at random data. Okay, so that was the general purpose of weighting techniques. So the idea there being, you construct these pseudo populations by reweighting individuals based on how likely they were to have made it, and then correspondingly, how many individuals in the full population should those individuals represent. Imputation techniques are perhaps a little bit more intuitive if you're not used to thinking about weighting, but they're going to be quite computationally intensive. And so the idea with imputation is that we want to estimate these missing values, these yims, based on the observed values, the yios, and the variates xi. So what we'll do, generally speaking, is we're going to compute the parameters of interest as though the imputed values were the truth. And then, in general, we're going to use what's called multiple imputation, which involves sort of estimating the values, computing the parameters of interest many times over, and then sort of averaging those to get our true estimates, right? So we're going to predict the values, we're going to use those predicted values to compute parameters, and then we're going to do that a bunch more times. And then when we average the results, we'll sort of get valid predicted values as long as we're filling them in a sensible way. So we need to choose whether we're using single imputation or multiple imputation, and we need to choose how we're actually going to be going about imputing. I'm not even going to spend any time thinking about single versus multiple imputation, and I'm just going to tell you, you should never use single imputation. It's just not effective. You're going to be underestimating your standard errors. You're not going to be using a technique that makes much sense. The only time that maybe you could use single imputation is if you're just trying to get a sense of whether your procedure is giving you results that sort of are reasonable. But in general, you should always be using multiple imputation. And so the idea is that we're going to perform this imputation process m different times, and each of those times we're going to estimate our beta parameter, right? So we get beta hat k for each of those k equals 1 to m estimation procedures. And then we can take beta hat to be the simple average of those. Now, the nice part is that we also can get an estimated variance of beta hat. And the way that we do this is through this kind of ugly looking expression here, but it's broken down into these two different components, where this first component is the average covariance of each of the different imputed data sets, right? So we get beta hat k from each of them. There's some way of estimating the variance there, and so we can estimate that and take the average. And then we have this second term here, and the second term is basically the correlation or the covariance between the actual values and the overall average, right? And so we can think about this as sort of adding on a covariance. Now, the thing is, if you actually look at this coefficient that we have out front here, then the coefficient there is going to sort of be going down to 0 rather quickly, right? You have m in the numerator, you have m squared in the denominator. That's going to go to 0. And if you have a process that doesn't have very much variation in it, then you're also going to find that that term is quite small. But we need it there just to sort of account for the correct correlation or the correct covariance of our estimators, right? So then the decision we have to make is, how do we actually perform the imputation? How do we predict the values? And in general, we're going to be thinking about fitting regression models to do this, right? So you could think about taking, say, at time 2, the expected value of yi2 given the first observed value and the covariates as fitting some GLM, right? So we have some link function g here, and then we have some set of covariates which are dependent on the first observation and any covariates that we actually have. And so we're saying that this link function is given by zi1 transpose gamma 2, right? So we can fit that GLM model, which gives us predictions for the observed values, right? So then we can write yi hat 2, which is going to be the predicted values based on the observed models for the first or the second stage. And we could use that to predict all of the values for those who we didn't actually observe. Now, in order to ensure that we're not using deterministic predictions, right? If you fit a GLM or you fit a linear regression model and you just predict based on the average, you're going to get the same prediction every time you run it, right? And so to ensure that we're not doing that, right? Because if we're going to do this multiple times over, we don't want to get the same predictions every single time, right? That would defeat the purpose of doing multiple imputation. So instead of actually using yi hat 2, what we're going to do is we're going to sample from the distribution, right? And so if you're thinking about a linear regression, right, then we're sort of thinking about that as being normally distributed. And so we'd sample from a normal distribution with a mean of yi hat 2. Or if this is if yi is a binary response and you've used a logistic regression, then yi hat 2 is sort of the probability that it equals 1. And so you can generate a binary response with the probability that it equals 1 given by yi hat 2, right? And so that's going to let you generate sort of outcomes, and you can fill those in for anyone who has missing values. Then we can repeat the process at time point 3, where now we can condition on yi1, yi2, and xi. And we can condition on that for those individuals that have missing values where we've plugged in yi hat for yi2, right? And so we can sort of continue this for all of the stages up to k. And then that gives us our estimated hat, or beta hat 1, and then we repeat this m times for the multiple imputation. Now, the problem with what we've just outlined here, this 5-step process where we fit a regression model, we sample from the distribution, and then sort of repeat, is that we're actually underestimating the amount of variability. And if you remember thinking back to your regression course, where when you're plugging in something that is a predicted value, you're going to end up with more variance than if you consider them fixed. The problem is that we're essentially treating yij hat as fixed values after we've estimated them, and that's not going to be the case. So instead, what we're going to do is this procedure of drawing our coefficients that we're estimating from their posterior distributions. Now, if you're familiar with Bayesian inference, then that sentence might make sense to you. If not, that's okay. You can think about this as saying, instead of our regression parameters being fixed, we're going to say that they have some distribution. And when we estimate them with our regression equation, we're estimating their mean and their variance, and then we can sample from whatever relevant distribution is, right? And so in practice, this is sort of, requires some Bayesian understanding, but the idea is that by sampling the coefficients to be random and then sampling from the distribution for our yi hats, then we're sort of correctly accounting for all of the variance that's there. Instead of using those predictions directly, there's this other procedure called predictive mean matching, right? And the idea is quite similar. So you're going to fit the regression equations just as we did before. So you're going to sample from the random coefficients, and you're going to use those to generate these predicted yij hats, okay? And then for every individual that's missing, we're going to say, take the kappa nearest individuals who had observed values. And when we're saying kappa nearest individuals, what we mean is we're predicting the value for all of the people, whether they were observed or not, right? Then we just look at the observed people and we say, which are the closest individuals to this missing prediction here, right? So if you predict that an individual had a missing value, had a probability of it being missing of, or a probability, or yij hat is, predicted to be 0.65, right? Then what you're going to do is you're going to say, for all of the individuals who actually had an observation, which were the closest to this 0.65? And kappa is just some number you specify. It could be 3. What are the 3 closest observations? What are the 10 closest observations? That's going to be up to you. But once you pick those sort of 10 closest observations, those 3 closest observations, you can randomly sample one of them. And then what you're going to do is you're going to borrow their observed value, and you're going to plug that in as your imputed value instead, okay? And so then you repeat this process for all of the j, and you repeat this m times. So the key difference here is that we're fitting the same types of regression models, but then we're using our predicted means instead of those predicted means to then randomly sample from the outcome distribution. We're using them to match individuals with those who actually had observed values. And this is going to have a sort of a couple of benefits over the standard regression technique. And the 2 primary benefits are, first, you're always going to end up with a value that was actually plausible, right? when you're predicting with a regression equation, you can always end up with values that don't make any sense. And that's because, our regression equations are just going to predict a value. They don't know what the underlying scenario was like. But if you're borrowing from someone who actually had their value observed, well, then we know that that was a possible value to observed. And we're basically just saying, you're the closest person in our data set. Why don't we just pretend like the observation was yours? The second benefit is that you actually can misspecify the model slightly, and this is still going to be valid. So in the regression case, you have to correctly specify the actual outcome model in order to make valid predictions. Here, as long as you specify a model which correctly matches people together, so when you're predicting them, as long as the people that you're saying are closest to your observed value are actually closest to your observed value, whether or not your predictions are sort of correct in the overarching sense, as long as you're keeping people who are similar close together, this is still going to work. So in general, we're going to prefer predictive mean matching, but I think the regression situation where you just fit progressive regression models and you estimate using them is sort of more intuitive. Now, for both of these, obviously there's, this whole idea of sampling from the posterior distribution, which is a little bit more mathematically involved than what we're getting into. But if it helps, the way that I personally think about this is that with these regression-based imputation techniques, we just fit a regression model to predict the outcome at stage 2 using the input at stage 1 and our covariates. And then we take those values and we pretend like they were observed. Then we fit a regression model at stage 3 using 1 and 2 and the covariates, and then we predict those values. With matching, instead of using the predictions directly, we're pairing off people who are close to each other and borrowing actually observed values. And then we just need to be careful, and that's where all of that sort of fancier math comes in to ensure that we're correctly accounting for all of the variability in the sample. But conceptually, it's just sequential regression models, and the R code is going to handle that for us. Now, the last point that I want to bring up in terms of imputation is that likelihood can sort of be seen as an imputation procedure itself. So we said that any of these likelihood-based procedures, as long as you've correctly specified the likelihood, will be valid with MCAR or MAR data. And the basic reason is that the conditional distribution given xi is going to be the same between just the observed people and just the missing people, as well as the full sample, right? And so in this sense, likelihood procedures are going to be acceptable. Now, you're also going to see in the literature, if you look out, people talking about expectation maximization, EM algorithms. And this sort of lets you explicitly make likelihood an imputation technique, and you can estimate the models sort of in a little bit more generality using these procedures. I'm not going to require you to fit expectation maximization, but I just wanted to point out that the reason that the likelihood is going to work with MAR or MCAR data is because it's actually sort of a subset of the imputation techniques that we're using. So if you're using a maximum likelihood technique, you don't need to think about using imputation directly. But if you want to use a technique that does not allow for likelihood interpretation, so if you want to use GEE, you can use imputation instead, or you can use the inverse probability weighted GEE itself. Okay. So as a general overview, that's sort of, the really fast way of handling missing data in longitudinal analysis. So missing data is a pervasive issue in longitudinal studies, and ignoring missingness at best causes a loss of efficiency, and at worst completely invalidates your analysis. So it's something you definitely should be concerned with. We can categorize them as missing completely at random, where the missingness does not depend on the outcomes, missing at random, where it depends on only the observed information, or not missing at random, where it depends on both the observed and the unobserved missingness. We can talk about monotone patterns, which everything that we saw today sort of assumes monotone missing, and you can try and think about how the imputation technique relies on this monotone missing, right? Because we have to fit these sequential models, and so if it's not monotonically missing, well, then you're going to end up having sort of an inability to predict all of these values for people because you're going to have sort of missingness and not missingness. But if it's monotone, we can impute exactly as discussed. And if it's non-monotone, there are other methods that are similar to what we talked about, but that just require a little bit more care in the models that you're fitting, right? If we're using complete case analysis or available data analysis, that's valid only under missing completely at random. We can use weighting techniques, which generate sort of pseudo populations based on how likely someone was to be observed in the population. And those are going to account for missing at random data. In particular, we saw how we can adapt the GEE estimating equations to weight each individual, right? And it's sort of the intuitive way that we're thinking about that is each person that we do observe is going to count for themselves, plus some people who are like them that we didn't observe because they were missing. We can think about imputation techniques, which we saw you can sort of just fit these sequential regression models and then predict the outcomes. And, we have to be a little bit careful about how we're accounting for the variances there, but at the base level, we're just thinking about a bunch of regression models end up predicting those values, okay? And so that sort of covers our discussion, our very brief discussion of missingness in these models, in these longitudinal data, right? So in the next lecture, we'll actually see sort of the implementation of some of these with an R package. And, we'll see how can we actually accommodate missingness and where do we actually need to, right? Because again, if our likelihood is correctly specified, we don't need to handle missingness at all. And so I'll introduce that to you. And that's going to be valid beyond the scope of longitudinal data itself. It's going to be valid sort of in any analysis that you want to run. And then after that, we're moving on to survival analysis. So we'll do one sort of wrap-up lecture on longitudinal data analysis. And then after we do that wrap-up lecture, we're moving on to survival analysis. So as always, if you have any questions about what was talked about today, I know it's a lot of information thrown at you, so definitely feel free to ask me. If you have any questions about anything we've covered in longitudinal analysis so far, I encourage you to reach out or ask on Teams. And otherwise, I will see you all in the next lecture.